Просто. Кто меня представляет?
את איתנו מ-2001, נכון? ואת עשית את קדן שכבה. זאת קדן שכבה. בדונייצק. מדונייצק. טוב, נשאר שם בכלל משהו. מישהו, ראיתי הרצאה לפני איזה שנה, שמישהו חוקר ואוקראיני. אומר, רק תמונה של בניין, זה הפקולטי אוף פיזיקס של, זה היה חרסון, זה היה חרסון. חרסון גם. כן.
עכשיו המוסד נמצא בשני מקומות.
So let's all take our seats, please, and we'll start on time.
באיזה שנה הראשונה?
97 התחלתי
So they have the great pleasure of introducing one of their own, the total unit of the Nanocharacterization. And this is part of our initiative that this Nano seminar will also have several types of content. There's the regular seminar format scientific content. There's also part of our mission is to educate our community, basically ourselves, about our new capabilities. And also you will notice that some of our talks have more of an industry orientation. And that I think is going to be the next talk, right? The talk now, which there will be a talk of one of our leading industry customers in the analysis. So now to Ina. Ina did her PhD in Donetsk, in the Ukraine, graduating in 1996. In 1997, she made the important step of coming to Israel, and she worked as a postdoc with Dai Shechtman at the Tecnai until 2001, right? Which is when she joined the Hebrew University, and she's been one of the founders of the Nano Center since I think Mary Popov, probably one of the longest standing employees. So thank you for that. And the real scientific and professional foundation of Nanocharacterization microscopy we have here. And today, Ina will talk to us about our new Talos F200i microscope, which is up and running, and she just signed the acceptance form last week. Yeah, 2 weeks ago.
2 weeks ago.
Scientific. So let's hear about the microscope. Ina, thank you. Please.
Thank you, and thank you all for coming. So the environment is too hot in all possible meanings these days. So hope, okay, it will be interesting for you to hear about our new scanning transmission electron microscope Talos F200i, analytical and high resolution. So a little bit about history. So okay, this is the instrument. This is the instrument. It is the installation was completed about 2 weeks ago, and I signed a partial acceptance on 29 of May. So a little bit about history. So this is not our first and not our second and even not our third transmission electron microscope, but this is the microscope Talos F200i. Replaces our good old Tecnai F20. So this instrument was installed in 2002, and from 2002 till 2008 it was our only TM, and then it was our flagship TM until 2018. In 2017 we acquired TEMIS. I will mention it at the end of the lecture, and from 2002 till 2024, F20 was our working horse in all possible means, in the applications of TM, of high resolution TM. It served as a multi-user instrument with well-developed analytical abilities, and okay, we dismantled it at the beginning of this year to replace it with the Talos F200i. I think this is at least the new microscope is at least 5 generations after our good old F20. So the instrument entered the same room. This is room number 109. In the ground floor of the Nanocenter building. You can see that the ceiling is the same. And okay, so this is about logistics. Since Talos replaces Tecnai F20, I'm going to present it as a comparison between the abilities we had and the abilities we acquired and maybe lost. We did lose something, but this is not something dramatic. And I would say, I think here most of you know that the images in TM and STEM are not as fancy as the imaging in the scanning-electron microscope. So, and the instrument I'm going to present is very young, so we didn't have enough time to acquire a lot of fancy stuff with our instrument, with this new instrument. So part of the images I present here are related to the evaluation at the thermoofficial scientific. Part of them are from the acceptance test, and hope in the future we will have enormous amount of images to show up. For a while, I am talking about the specifications and the comparison about comparison on what we had and what we added. Okay, so first of all, both instruments are with the field emission gun, but what we had was the Schottky type field emission gun as fed, and what we installed is ultra high brightness cold field emission gun. So first of all, the warranted service life of Schottky is typically 1 year. Of cold FEG is expected to be at least 5 years. So this is a sufficiently different lifetime. But the most advantage of the cold FEG is its brightness. So it's much brighter, at least 1 order of magnitude than the Schottky FEG. And the energy spread is only 0.3 versus 0.8 we had. This means that the electron beam is highly coherent and bright. That means we have better spatial resolution, especially at low accelerated voltages. So the microscope can work from 200, so the new microscope can work from 200 kilovolt down to theoretically 20. For a while we have 2 alignments at 208 kilovolt, but depending on the needs we will proceed to lower voltages, and we should not lose the resolution because we have a highly coherent and bright electron source. Of course, it helps to make the STEM acquisition, the scanning and transmission electron microscopy, faster, easier, and provides higher resolution. And also the quality of spectral data should be much higher with the Talos because we have more electrons per unit area. So we excite with a denser flux, and we can get a higher flux of X-rays, for example, and we will see it. So next, as a result of these advantages and development of a more stable and more advanced electron optics, with Talos, we have improved resolution in the TM mode. So the numbers do not look that impressive because we already had 1.4 angstrom and now we will have better than 1 angstrom. But if we are talking about the materials, it makes a sufficient difference. And on top of that, we have much better detector for TM acquisition. So what we had was 1K by 1K YAG slow scan charge coupling device from Gatan. I would say it was advanced 25 years ago. But from that time, so the maximum speed of this acquisition was only less than 25 frames per second. And the pixel size was 25 microns. So we had quite small field of view, slow detector, and its sensitivity was not high enough to apply, for example, low-dose imaging. With the new instrument, we have CETA CMOS sensor, 4K by 4K camera, with a quite impressive acquisition speed, with small pixel and highly sensitive phosphorus coating. So what we add with these abilities is sensitivity and acquisition speed and wider field of view on top of higher resolution. And here I show you the images which belong to the group of Professor Leo Zivgar. The samples were from Tal Benjamin. So these images were acquired not with our instrument, but with the same instrument during the evaluation at the manufacturer lab. So what we see, this is an image acquired at the colloidal perovskite, cesium lead bromide. So the material is typically extremely highly sensitive. So it is so beam sensitive that it is not easy to acquire a single frame. So it degrades in due course of the acquisition. And it comes with the organic solvents and ligands on top, so the contamination rate is also very high. So here the sensitivity and the acquisition speed is even more important than the resolution because the lattice is not that small. So this is not gold and not iron. This is a compound with quite large interatomic distances, but what we see that we can get quite nice image with the resolution of 0.18 at least, and with high contrast with this new CETA camera and with a very high speed. So the image was acquired during less than 1 second. And also because 4K by 4K matrix, the option is to acquire the large field of view and then to go digital magnification. I will show you in the second slide, I think. Make the digital zoom. Enough pixels means we will get a full resolution image even if we acquire quite large field of view. So this is another a pair of images acquired at the similar sample, even less stable than the first one. So and you can see that it is not hard to get to the lattice image if the particle is properly oriented. And now, okay, this is the image acquired with our CETA camera, with our microscope on the standard gold palladium cross grating replica. 4K by 4K, 1 second. Okay, let's see. Okay, and we can zoom in, and you will get all the information stored in each pixel with quite high contrast, 1 second, 4K by 4K. So this is the strength on the new detector for TM and improvement in the TM resolution. In addition to these advantages, fast camera means we can allow ourselves a dynamic experiment. So we acquired, in the configuration of Talos, we purchased for the first time in the whole history of the UNC, we purchased a detector, a holder for dynamic experiment for in situ heating and in situ biasing. So this is a detector which allows in situ heating up to 1200 degrees. In situ biasing, it is EDS compatible and it allows high angles. But what is specific about this detector is that it uses MEMS support as the holders. So this is not a holder. This is not a holder with the standard TM grids. This is a holder with a MEMS device which should carry the sample. So that's why I mentioned here in the slide that for each specific sample we need to find the way to deposit the sample on this support. But it's doable. According to it's not a problem with the colloidal dispersions for sure, because this is only a drop casting. But if we are talking about the focused ion beam lamella and other solid samples, there is a way to do that, but we need to solve for each specific sample. But it's doable, and the heating rates are enormous, from very, very slow, like 100th degree in second to 100 degrees in second. So it's quite flexible, but we are starting. So this dynamic experiment was not available with our old TM, and it was not available with any of our TM because we didn't have heating holders. So the only dynamic experiments we succeeded to do in the past with F20 was acquisition of the coalescence of silver nanoparticles on grid with using not the main detector, the Gatan slope scan camera, but the TV camera and the home DVD recorder. So now we can acquire films, movies about, for example, transformation of the central structure under heating and under cooling. So this is a cooling from the target temperature down to room temperature, but controllable. Okay, this holder allows controllable heating and cooling and biasing. Okay, so now we are coming to the scanning transmission electron microscopy. So in the past, when we acquired F20, it was fully blown dream configuration with everything that was available at that time on the market for high resolution and analytical TM. Okay, so at that time, what was available was only one STEM detector, high annular dark field STEM had. So our TM had only one STEM detector, limited by the information, we will talk about that later, and the matrix was 1K by 1K, and the resolution in STEM mode was attainable. So in the specs, it was written attainable 1.5 angstrom. Okay, so that practically means that for gold, for example, we didn't have enough resolution to get the lattice image in STEM on gold. What we succeeded to do, the lattice image in STEM on semiconductors. So the larger is the lattice parameter, the better. With our new Talos F200i, we have easy 1.36 angstrom. That means this kind of image. Okay. So the dumbbells labeled here in the yellow ellipse are the atomic columns of silicon atoms in the lattice of silicon oriented with the 110 parallel to the beam direction, and the separation between these two columns is 1.36 angstrom, and it is clearly visible. It is even relatively easy. And more, I will skip for a while. Let me show you something else. Okay, and this is the high resolution stem with HUJI on the standard gold grating replica. So the replica is a gold palladium clusters on carbon. So what you see, the lines you see are the periodicity, the high resolution, atomic resolution image of gold palladium cluster, and the distances you see here are mostly 2.3 and 2.0 angstrom of the gold lattice. So this is something routine, more or less routine with this microscope. This was totally impossible with F20. So we gain here a huge amount of abilities with the high resolution scanning transmission electron microscopy, because the resolution and the easy of acquisition is much more advanced than we had with the F20. But not only this gain we have, so the acquisition speed is also faster, and we can acquire that. I mentioned there that we can. This image was acquired at 100 pica-amp of current, with a quite coarse matrix 1 by 1 K, with a dwell time of 20 microseconds per pixel. Okay, so this is the gain in the resolution of the STEM imaging. Okay, the matrix available with STEM imaging is now 4K by 4K, the maximum matrix. That means that we have wider field of view, as I mentioned in the TM as well, and we have much more. Now we don't have only the only STEM detector with a limited information, but we have a set of STEM detectors, the Panther STEM detection system, composed of the segmented bright field and dark field detectors on top of the HUJI. So we have much more sensitive and advanced HUJI, and in addition we have one bright field STEM detector and a few dark fields. So I mentioned two, but depending on the working distance, it could be more. Here I show the design of these segmented detectors. So the segments in the detectors are radial and quarters. What we get with this kind of detection system is, let me see, a lot of complementary data, a lot of data which was not, okay, we acquired the STEM images. We acquired them, but typically what we had in the STEM image was mixed Z contrast, the contrast of the element, mass thickness, and diffraction, and the only way to distinguish between these contrast mechanism was walking distance, so camera length. That was the only way, because we didn't have a control over the angles, so we were able to change the acceptance angle of the detector only by magnifying and demagnifying of the diffraction pattern of this detector. With our new detection system, we have all these contrasts, but we can separate these contrasts one by one by simultaneously acquiring. Okay, let me see. Okay. So simultaneously acquiring electrons scattered by different angles on the detectors having different acceptance angles. So this is the scheme of the STEM detector with a radial separation. So this is the annular dark field detector. So, and we have a few segments, radial segments on this detector. So when we scan the sample with a beam, we may acquire a series of images at these images from the electrons scattered by this angle range, and by this angle range. And in addition, with the bright field detector on axis, we can acquire the electrons scattered along the optical axis. So when this beam scans the material, the electrons are scattered due to numerous interactions happening in the material. And with our previous configuration, we always acquired only those electrons which were scattered by high angles, because the HUJI is a big hole here and only one angle range outside. With our new detectors, we can do the same thing. I think part of you is familiar, which we already do with our SEMs. We have, I think, from 2010, we have radial stem detectors, which we may employ for almost any angle, any range of scattering angles. Now we have the same configuration and even more advanced with our TM. And here is the example of the complementary data. So this is here and here, we see the same sample. So gold palladium clusters on carbon are here, acquired with high annular dark field. And what do we see here, in addition to the atomic resolution in the gold palladium lattice? We see here the contrast, which is called high Z contrast. High Z contrast because we have extremely heavy clusters of gold, extremely heavy because gold is number 79 and palladium is number 86. And the contrast in this image is roughly proportional to the Z, to the square of Z. Okay, so, and the dark regions we have here are from carbon, because carbon is only number 6. So the contrast here is high Z contrast due to the heavy elements. And this is what we typically had in our previous configuration. Now we take this material, change the detectors, acquire the image with a pair of bright field and dark field stem detectors. Okay, here is the bright field, here is the dark field, and what we have here is a lot of gray levels, and these gray levels tell us a story about the structural defects in this cluster. And this story could be done even with the atomic resolution, but currently what is interesting is that we have complementary data. So we can distinguish between say multiple twinning and parallel twinning here. And here we have mostly diffraction contrast and less mass thickness and less Z contrast, because the acceptance angle of these detectors was tuned to the diffraction angles by the gold lattice. So this data was totally unavailable with our previous configuration, and this is only one small and quite quick example on what could be done, because the complementarity of the data always allow to tune the contrast and to choose the information we need with a very high flexibility. It is not the case when you have only one stem detector. And in addition to the okay, so this is due to the radial segmentation of the detectors. And this is due to the quadrant segmentation of the detectors. So this is something completely new in our working force instrument, but this is what we already have with our high-end tennis. So this contrast, we can acquire the contrast, which is called differential phase contrast, by using separate, so to acquire this, the electrons coming to different quadrants of the detector simultaneously, but separated by the quadrants, and then we can subtract one from another. And what we will have here is the image of the inner electrical field in the material, or inner magnetic field of the material, which may shift the spot of the collected electrons over the detector, depending, so if it exists. So if there is an inner potential in the material, electrical or magnetic, it shifts the beam over the detector, and this shift could be acquired when we acquire the information quadrant by quadrant and subtract left from right. Okay, and this is the example of such imaging. Okay, Sergey in the past, I think, made a few experiments of this type, and we will proceed with these experiments with the Talos. For a while, I have only explanations about how it should work. But this is the way to visualize magnetic and electrical field inside the sample. So this is more gentle and much more exotic contrast. We have, and we have it due to the specific design of the detector. And in addition, there is a way to make the integral differential phase contrast. And this way allows for imaging of low element atoms at the atomic resolution. So in general, imaging of atoms of low elements is a big challenge in the transmission electron microscopy and in the scanning transmission electron microscopy. Just because the scattering amplitude from these atoms is much lower than from all others, it is a big problem to do that. With our new microscope, we have a few options, at least 3, to image the atoms of low elements in the lattice of material at atomic resolution. So one is annual dark field imaging with STEM. The next one is the IDPC contrast. And there is also a way to acquire the EDS map with a high sensitivity at high collection angle. And I will show you the example in a few minutes. So this is the gain we have with this new microscope. A whole world of the multimodal STEM data. No one needs all these abilities in his or her experiments, but it's really flexible and it could be applied to extract a lot of information from the material which we previously didn't have the way to get, and everything I show here is simultaneous. So you can acquire the simultaneously different contrast mechanism on the material while scanning it with extremely low current and doing it fast. So that's the big advantage we received. Okay, and now we are coming to the analytical. Here is, I will start from the losses. Our new configuration has no yields at all. So the energy filter TM became a big problem because there was only one monopolist manufacturer of the electron energy spectroscopy attachment, the American company Gatan. With the time, they increased their prices enormously, and then arrived a few competitors with a few optional, with a few systems under the development. So it was not a good time to acquire electron energy loss spectroscopy, and the decision came without a lot of doubt, just because we already have electron energy loss spectroscopy at TEMES. That's why we are not without yields. And we acquired the configuration adjusted for future attachment of EELs if there will be a good option. If we will have enough budget, we will extend our analytical abilities towards electron energy or spectroscopy. But for a while, we do not have this option as compared to our F20, where we had full GIF, so electron energy filter TM and the spectroscopy and the TM and scanning. But what we got with the F20 is enormously sensitive EDS system. Not the EDS detector, but the EDS system, because the system is composed of two detectors, two retractable stem detectors. This is the configuration. So the detecting crystals are shown here in green. So this is the holder of the TM, this is our sample, and the shadowed area is a practical area in which we can acquire the X-rays, and this area gives us more than 1.7 steradian versus less than 0.4 we had with our previous system. The spectral resolution is also better, and the size of the crystal is much larger. So we have SSD, so solid state detector, Peltier cooled, with a large detection area, with a nice spectral resolution. Still, we cannot distinguish between the titanium L and nitrogen N, but the overlapping is of some elements is much less painful now, and the algorithms for deconvolution are much more powerful. And the key point here is the collection angle. The collection angle is so high, it could reach even 2.55 steradian. So this means that from very, very small and thin and tiny sample, we can acquire almost each X-ray photons emitted. So with our high brightness gun, we can scan with picams and with nanoarms. So we can generate a lot of X-rays. From the tiny region, we can collect almost every photon, and we can do that at any geometry, because unlike the previous configuration when we had to tilt the detector we had to tilt the sample towards the detector, now we can tilt as much as we need to orient the sample, but it will not affect the collection ability. And for example, if we have the interface and we orient it so that we see it parallel, the interface plane is parallel to the electron beam, we'll acquire EDS at this position without thinking about how to increase the amount of photons or something like that. And as a result, still these maps were not acquired at our TM. We still didn't have enough time, but these nice atomic resolution EDS maps were acquired at the same instrument. And this is a strontium titanate sample oriented properly to see the lattice image. And if you take care on this map, so this is the map of oxygen. So this is our third way to image the light elements at atomic resolution. So after any reduction and IDPC contrast, we also have this EDS ability. I would say our previous ability was nothing as compared to these results. And here you have a few more examples of mapping the different compound oxides at atomic resolution with EDS. Okay. In addition to all these sufficient things, resolution and the acquisition speed and sensitivity and the strong analytics, the instrument is totally different from the F20 because it is fully digitized. So this is a digital instrument with full remote control. So the apertures are motorized. The rotating TM detector is not the analogous screen, but the smart cam So the instrument is operated from the PC. So the operator looks only at the monitor. No more sitting near the column, no more switching light in the room, okay? And the instrument is extremely stable. So the optics, the constant power lenses, and the optics electronics is stable. So, and a lot of new software. That's why the instrument is, I believe, much more user-friendly. It allows full remote control, and it is stable. In our case, however, we don't have space for remote control room like we did it with the tennis. That's why the remote control station is from inside the room. So this is the table for the remote control, but still the operator sits with a back to the instrument, which is quite unusual for those who used to operate our F20. So as I already said, the instrument was partially accepted on 29th of May. There are a few features which are under development, and this is the artificial intelligence alignment system, AlignG, which is going to be implemented soon and should help our entry-level users to handle the instrument with all its abilities without big headache. Okay. As I said, it is going to be our working force from now and I believe next at least 15 years. So as I mentioned, we already have alignments for 280 kilovolts, and depending on the applications, we will proceed towards lower voltages. Okay, our current fleet of TMs is not only this new instrument, but we have two more transmission electron microscope. So this is our good old 120 kilovolt cryo TM, Tecnai F20 Spirit. Yael is responsible, Dr. Yael Kalisman is responsible for this instrument. Oops. Okay. And this instrument works in two major applications, big and totally different. It is our, for a while, only cryo TM, only working cryo TM, okay? And this is an instrument for quite a straightforward monitoring of chemical reactions, widely used by a lot of people presenting here. Okay, and this is our high-end aberration-corrected scanning transmission electron microscope, TNS-Z. So Dr. Sergei Remennik is responsible for this instrument, and this instrument may work from 60 to 300 kilovolt, and is located also on the ground floor of the Nanocence building in the room number 101. Okay, coming soon. We purchased our Talos, not alone, but it was a big package deal, and actually we purchased two transmission electron microscopes. The microscope which is going to arrive at the end of 2024 or at the beginning of 2025 is called Glacius 2. So this is absolutely state-of-the-art advanced 200 kilovolt cryo TM. Yael will be responsible, or is responsible for this instrument. Currently it doesn't have an address because the room, the building is to be reconstructed, and we are just at the beginning of the of the planning, I would say, or before the decision on the budget. But that's why I'm not sure when the instrument will arrive, whether it will arrive as agreed during the purchase in December 24 of this year, or somewhere in the next year. But this is the instrument, and I hope soon you will hear about the details of this instrument. coming back to our new Talos F20. As I said, the images of TM and STEM are not that fancy, but they are not pictures anyhow. They are not pictures, and this is my crazy idea, which I go from lecture to lecture. Please, when you think about the TM analysis and STEM analysis, don't think about picture and don't think in the terms of aesthetics. This is, you should think about the beam specimen interactions, about the information you wish to get, about the contrast mechanism underlying the appearance of features in the in the image. So this is data. Actually, what you acquire is data. You always acquire data, and this data is this is the data about the 3D sample. Even the thin sample in the TM is 3D. It is at least 100 atomic layers thick, or in most cases, it is more. So the scattering of the electrons happens inside the 3D object, and the data is acquired into the 2D detector. And it is presented as a 2D matrix in the gray levels. Typically, with this new microscope, we have at least 16-bit depth, meaning that there are 64,000 gray levels in the image. And that's it. Nothing is beautiful. All you get is information. And the main aim is to extract as much information as you need about your sample with this smart instrument. And also remember that the preparation of the sample always introduces artifacts. Always. Because at least this is a vacuum system. At least you deposit your sample in the open air and you enter the vacuum. But this is the least change that happened, and you should take care about this as well. With that, I wish to thank you for your attention and welcome to Talos. Training will be announced around August, I believe. These days we cannot get an application training on site because we are in the middle of war and nobody knows when the people from abroad will be ready and permitted to enter our region. And if you wish to discuss something and for service, please contact me or Sergey. Thank you.
Well, I have to watch this up, so I'm pressing him. Questions?
Ina, thank you for beautiful presentation. I'm sure it's going to be a great instrument. With the F20, we had few, but we still have few independent users. Do you expect to have independent user also for this instrument?
Sure. This instrument is so smart that unlike F20, one user cannot affect the alignment of other users because they are separated. So this is the instrument built to minimize the effect of multiple usage on the performance of the instrument. Still, it needs training. So we are learning how to operate this instrument now. It will take some time, and yes, for sure, we will open this instrument for multi-user operation, but not immediately because even if the instrument is very smart, it doesn't think instead of the operator. So the operator should be smarter, and the trainer should be smarter than the trainee to be able to teach something. So that's why it will take some time, but the plan is for sure to open this instrument for multi-user operation.
More questions? I have a scientific question, but maybe we can split one.
Okay.
Okay.
So everybody knows that they ask questions later on. Okay, thank you.